Engineering from New Jersey Institute of Technology in 2012. During a PhD from July 2008 to December 2012, he worked full-time at NREL USA through the joint collaboration of NJIT with NREL. From January 2012 to September 2013, he worked as a postdoctoral research fellow at the Department of Electrical Engineering of University of Arkansas, and from December 2013, he has been a postdoctoral research fellow at Sandia National Lab. His research interest includes fabrications and modeling of semiconductor device like solar cell, MOS, and thin film transistor. So I request Dr. Budharaja for presenting his seminar. Dr. Budharaja.
Okay. Good morning. Good morning to all of you, and I consider that you all are listening my voice properly. Thanks Dr. S.P. Das for giving the introduction, and here is my talk in thin film silicon solar cells, and here are the affiliations like UTAP is my present place where I am working, Sandia National Lab, and my past affiliations are the Green Research Center and University of Arkansas. And you, in the earlier session, you listened the nice talks by Professor K.L. Chopra, Professor Chaitanya Solanki and Arul, and you get very good overview about the thin film solar cells, about its market. This talk is less market and more focus on research, but research always give the applications to the market. So I consider that this will be helpful. So the title of my presentation is the Design and Fabrication of Fishnet Structure to Study the Plasmonic Effect in Thin Film Silicon Solar Cells. And here are the list of my group members, Liming Z, Sayansin, and Professor Vasuvardhan. I move on to the slide 2. So here are the outlines of my presentation. First, I will start from the current trends in thin film solar cells. This will match too much what you have already listened by earlier 3 speakers, and then we'll see the problems in thin film silicon solar cells. After that, we'll see some solution, what solution we are proposing in our research work. We propose the use of the plasmonic effect. We'll see the details of that in this session. And after that, I'll show some modeling results, which is the designing of fishnet pattern, and the experimental results, which is the how we process the fishnet pattern to see the effect in thin film silicon solar cells. And finally, I will conclude my talk. I move on to the slide 3. So the current trends in thin film solar cells. The thin film solar cells have a very bright market, as you see in the previous talks. So in thin film technologies, there are major 3 technologies exist, that CIGS, cadmium telluride, and amorphous silicon. Our focus is mainly on amorphous silicon. So the figure on the left side, you can see how the market grows year by year. From 2009 to 2012, of course, crystalline silicon is a major role. It's dominant over other technologies, but you can clearly see the graph of thin film solar cell, the percentage, it's increasing with respect to the previous years. And those are the features which give lot of interest to go in this technology. And here the table that shows the best research cell efficiencies on CIGS, cadmium telluride, and amorphous silicon solar cells. And you can see that these efficiencies are approaching towards the crystal silicon, so it is promising to replace that technology. In amorphous silicon, is still a lot of problems are existing, but you can still work with this and solve those problems, and it get good place in the market. So the next generation photovoltaics will be thin film based, and the thin film solar cells, they are the better alternative to crystalline silicon solar cells. The installation of thin film solar cells, that tells that with respect to the previous years, how it's increasing day by day. It's it's okay that the solar technology cannot totally replace the production in comparison to the coal and oil and other natural gas, but with the year it's very environment friendly, so it can totally contribute in one sense, even if the percentage is very less, but it has some useful contribution. So the figure on the left side, it shows that with the year it just increased in terms of the percentage in terms of the production by different countries, and in globally it's valid perfectly. On the right side you can see it just shows the percentage, 83% that respect to the crystalline silicon, but in other thin film technologies they are just growing day by day, and with the time it's just increasing. So why it's happening so? Because of the several advantages. So here are the advantages of thin film solar cells which are based on silicon. That is, it has a low cost of in terms of the dollar per watt. It has a large area deposition. So it can easily grow on the large substrate. The world's biggest solar module has been produced in amorphous silicon. It has the low temperature processing because of the PECVD technique. The thin film, I just want to make clear, the thin film doesn't mean the thickness of any layer. It means that the deposition, it's follow all the deposition techniques, that all layers, they are just deposited. So it has the low temperature processing. That has one advantage. It has the high VOC because of the use of high band gap of the material, and it has high temperature resistance. It means that with the temperature, how the cell parameters vary. In crystalline silicon it happens more, but in amorphous silicon and in other thin film based silicon, thin film based solar cells, they have high temperature resistance. Even though they have several advantage features, there are some problems also associated with this technology that affect the efficiency to be lower. So on the left side, I show the schematic of the amorphous silicon based solar cells. So it has the A0 layer and then PIN. You can see P type and intrinsic and N type. The intrinsic is the absorber layer, which has a major role in the performance of amorphous silicon solar cells. So this is the schematic, so that one can get the idea about how this junction happens in amorphous silicon solar cells. So now we see the major problems. The major problems are the light induced degradation that happens in amorphous silicon solar cells. That happens because when you illuminate the solar cell, it creates some defect levels which act as the recombination centers, and that reduces the efficiency. So this is also called Stabler-Wronski effect. So due to this, what happens in amorphous silicon solar cells, once you make the solar cell and when you illuminate it, first it degrades and then it becomes stabilized. So efficiency always reduce and then become stabilized under the illumination. So that is the major problem in amorphous silicon solar cells. Another problem is the low minority carrier diffusion length, because these layers, the P-type and N-type layers are so thin and they are the amorphous material which has the high impurities present. So the diffusion length is very less. Third problem is the high recombination rate in different layers. So because of these problems, the efficiency of these solar cells are less in comparison to other technologies, mainly on crystalline silicon. So the one way to improve the performance of the solar cell is to enhance the absorption in absorber layer. So in this technology, the intrinsic region is the absorber layer that is made to be very thick so that it can have the sufficient electric field. So if you have good absorption in this layer, the efficiency of the solar cell will increase. So by this way, by increasing the absorption, one can increase the efficiency. So we work in this direction, and we saw that there is one solution to increase the absorption. in the intrinsic layer? The solution is the use of the plasmonic effect. That plasmonic effect consists of a nano pattern. So you can see the figure which is on very left, that is the PIN solar cell with the back and front contact. So what we did, we use the nano pattern and we give the name the fishnet pattern. So that fishnet pattern has the power of the light scattering. So we use this nano pattern, this gives the plasmonic effect, and when we use this nano pattern, the light which comes, the incoming light which comes, and when it comes to the back end, it at the back spacer, it just scatters the light and increase the absorption in the eye layer. So this fishnet pattern gives the plasmonic effect because it works as a plasmonic frequency. So what happens, that light scattering, that increases the path length by 4n square, where n is the refractive index, and the resonance frequency of the metal nanoparticle, it's just calculated as lambda by n, and it enhances the absorption by scattering of light. We'll see more detail about it in the next slide. So in what we did the modeling of this fishnet pattern, means how to optimize the fishnet pattern, means like the size and the width, the line width of this pattern, how it is optimized. So for that we did the simulation. So here again in the figure you can see the silicon, the thin film silicon solar cell. We give the PIN layer attached together and call it one semiconductor layer, and we make the fishnet pattern, and we first simulate it to optimize the line and the pitch size. So for that we use the finite element HFSS, which does the electromagnetic modeling, and that fishnet pattern is exploited to tailor the resonance frequency as in LC resonator. So what it does, as in the LC resonator, it has some resonance frequency. So this pattern also creates that resonance frequency. So at that resonance frequency, it resonates the light and it enhances the absorption. There's like impedance matching condition is required, and there are some other technical details like geometry and material properties that control the resonance frequency. So next we see the results of the light absorption increase by the use of the fishnet pattern. So we see that when we use the fishnet pattern, so with fishnet, it enhances the absorption. So what we did, you can clearly see in this figure that the increase in absorption happens between 600 to 700. So what happens, that we resonate the frequency so that it gives the enhancement in absorption at these wavelengths. So we concentrate on these wavelengths because at lower wavelength and at other wavelength, the absorption is already very high. We don't need to increase the absorption, so we design the fishnet pattern and simulate it so that it just gives the resonant frequency at the wavelengths between 600 to 700, because at these wavelengths the absorption is low. So to increase the absorption, we use the fishnet pattern and it enhances the absorption. So the figure on the right side, it shows the absorption in each layer. Each layer means you can see in this figure there are like different layers. So we calculate the absorption in each layer so that we can show that total absorption what is coming out of a solar cell is due to the absorption in amorphous silicon, because our aim is to increase the absorption in amorphous silicon. That's why we show this figure which says that the total is shown by the red curve, and in the amorphous silicon layer it shows by this blue. So that says that it covers most of the total absorption, and in rest of the layer it's very less. So that's why 92% of the total absorption is in amorphous silicon, which is our main aim, and rest other is being losses in other layers. So here, this figure shows the interference study in fishnet pattern. So in the fishnet pattern, what it happens that now I move on to the next slide. So this figure shows the electric field localization at different layers. So left side figure shows the top surface of the fishnet, and the right side figure shows the overall the solar cell. So on this picture, it says that more energy is absorbed by the amorphous silicon. So what happened, the scattered surface wave and the incident wave that interfere constructively at these locations. So at these locations, the electric, that's why at these locations the electric field is high. So because of that constructive interference, it has the high electric field that's associated with the absorption. And what actually happens in our simulation, we didn't follow the Beer-Lambert law. One can say that, okay, so you don't see the video. Okay, now it's okay. So you can say that absorption reduces with the distance, but we don't follow the assumption. That is some assumption that comes from Beer-Lambert law, but we plot the actual absorption that has been calculated in each layer. Now we see the experimental results in the processing of fishnet pattern. The earlier results, those were the modeling results. To see the reliability of modeling results, we pattern the fishnet array. So fishnet is a uniform array of the nanoparticles. So we did the fabrication part of it. So here are the processing steps. We deposit one by one layer, and to pattern the fishnet, we use the electron beam lithography system, and the metal layers were deposited using thermal evaporation, and AZO layer for the top and back contact was deposited using D3 sputtering, and for amorphous silicon we use the plasma enhanced chemical vapor deposition. So this is the design pattern come from simulation, and these are the SEM. So we after optimizing the processing condition, we got like good line width, and which had the good selectivity and good pitch. Pitch is like center to center spacing, which is required in the designing. Next, we did the measurement of the total absorption in a solar cell. So this figure shows the total absorption with and without fishnet. So with fishnet, the absorption increases, and it increases between 600 to 700, and it has a good increase. So next, what we did, we calculate the power ratio. So this power ratio is like about the how much is the total power and how much is being absorbed in the amorphous silicon. So that tells something that it has mainly in the amorphous silicon. This calculation is done because it is always being asked that whenever you have the absorption and you say that your absorption is increased because of the fishnet pattern, it may happen because of the other layers. So to show that reliability, no, it's only because of the amorphous, because it is only happening in amorphous silicon. You have to show some results which are related to this. And in the next figure, in the next slide, it shows the absorption, transmission, and absorption in different polarizations. So the transmission curve. The purpose to show the transmission is that the transmission value, you can say it's very, very low. So the assumption, like the absorption is like 1 minus reflection. It's mainly due to the reflection is become very important because the transmission part is very, very low. And the absorption at different polarizations, they have the good matching, and the reliability of the pattern was very good and has been checked in several samples, and it was, the results were very repeatable. Next, we did the electrical measurement on the PIN junction, and we see the quantum efficiency. The quantum efficiency plot at different wavelengths tell that with the fishnet, again it has a significant increase. And in the JB characteristic, it again show the enhancement in the JFC with the fishnet and the without fishnet. At VOC, we didn't see much change because in the amorphous silicon bandwidth, it doesn't have much change. But with the change in JFC, the increased value in JFC, that tells the increase in other cell parameters, which is like fill factor and the efficiency. So in this table, we see that without fishnet, the currents come out to be something 11.75, and with the fishnet in different samples, it has increased in all cases. So overall, like 30% enhancement in GSC achieved on an average. Next, we did the comparison between experimental and simulation results. So the figure on the left, it shows the HFSS model. Hello? Yeah. So the how much time I have left? Okay, so I'll just continue. I will finish it very quickly. So the figure on the left side, it shows the HFSS model. So this figure tells that we consider the roughness due to the fishnet pattern that was also being considered in the modeling calculation, so that we can compare perfectly the simulation and measurement result. So the simulation and measurements result were compared, and it has the good agreement in some regions. So at the wavelength around 681 nanometer, from like 650 to 700, we can see there is like some difference in the peaks and at the values. So the possible reasons behind this difference is like surface roughness in different layers were not modeled, because we calculated the surface roughness after the fishnet pattern, but the surface roughness in different layers, that were not possible. That's why we could not include in the model calculations, and the simulations were carried out for normal incidence, and the measurements, the maximum it can go up to like 15-degree angle in the ellipsometer. So that's why we can say that there is some differences are coming in the values, but the peak locations, they are perfectly matched. So it has overall good increase in the absorption, which is helpful to increase the efficiency of solar cell. Here are the conclusions of my talk. So one way to improve efficiency of thin film solar cell is to increase the absorption. The use of fishnet pattern, the plasmonic, has a capability to enhance absorption in thin film solar cell, as we see that the fishnet pattern that has a plasmonic effect, which showed the increase in absorption. The fishnet pattern that was designed that provide the plasmonic resonance, and the design of fishnet that was optimized through modeling, and it was verified experimentally. So with the use of fishnet pattern, the current density increased by 30% and absorption increased by a factor of 12.8. So we can say the inclusion of fishnet pattern has a perfect capability to improve the performance of thin film solar cells. Next, here are some acknowledgements. We acknowledge the research support provided by National Science Foundation. And second acknowledgement is the collaboration with Dr. Chui group at University of Arkansas at Little Rock. They provided the samples and they did the easier deposition for us. Thanks, and I'm ready for questions.
I have one question. I'm also working on plasmonics, and what I realize by my simulations is that if you put a layer of AZO or any other metal oxide over the structure, the plasmonic structure, then the electric field in the active layer, the intensity reduces. So we have to optimize the thickness of, like in your case, there is a azo layer even above the fishnet structure. So did you have to optimize its thickness, and what was the effect? Like, did it reduce the enhancements by putting azo? Why did you not directly put the structure in contact with the active layer?
Can you please give your introduction?
I'm Devika Kataria, and I'm a PhD student at IIT Kanpur.
Okay. Okay, so yeah, so you asked that did I optimize the thickness of azo layer? So yes, we optimize all layers. As you can see, so these are this is the modeling result. So the absorption is calculated in each different layer. So it is being calculated each different layer. So you solve the when we did the electromagnetic modeling using HFSS. So each layer you have to optimize it. You have to put the properties of it, and then the field confinement, it can be calculated in each layer. So the total absorption will show the effect of overall as a whole. So I would suggest that you should try in each layer. So yes, we did the optimization of azo layer and of course fishnet pattern. So
Pattern directly in contact with the active layer?
Active layer, you mean like the absorber layer? Yeah, it affects. Means everything has its effect. All different layer that has all its effect overall. So to choose that thing, you cannot ignore. So in the modeling, you can sometimes it happens when you do the device modeling, you just consider PIN layer and consider the surface layer. But whenever you do the electromagnetic modeling, the reason is, okay, I tell you the reason, because when you have the actual calculation, you don't follow the Beer-Lambert law. That tells like the absorption increases exponentially. So when you do the electromagnetic simulation, light passes through all different layers. So each layer has its thickness, so which should be optimized. Did I satisfy? I don't know. So, but yeah, you have something more. You can send me email, and then I will give you more details about it.